Okay, so now we start discussing the thermodynamic behavior of Fermi gas. Thermodynamic behavior of Fermi gas. So this is pretty similar to the kind of derivation which we have done in the case of Bose-Einstein gases. So I would suggest that first of all you should be viewing the complete set of videos for the Bose-Einstein gases before watching the videos on Fermi gases, because it's assumed that you have already watched those videos and then watching this video. So therefore I will be skipping certain things which might have been common to both the Bose-Einstein and Fermi gases derivations. So with that pretext, let's start with, much previously we have already written the corresponding expressions for the Fermi gases, right? For Fermi gas, we have the PV by KT is equal to ln theta is equal to sum over ln 1 plus z e raised to minus beta e, right? This is quite different from the expression which we had for the corresponding Bose-Einstein gas, and this is for the Fermi gas. And also we have n equal to sum over e. Now you know what does the average states means by. So sum over Ne is equal to sum over 1 by z raised to minus 1 e raised to beta e plus 1. So we had some equation number there probably, but now let me put new expressions over equation 1 and 2. What else? And we know that beta is equal to 1 by kt and z is equal to exponential mu by kt. All these stuffs we know. There in the case of Bose-Einstein, we had some limitation for the z values. Hope you remember that. But here we don't have any kind of such limitations, and therefore z can vary from 0 to infinity. There it was from 0 to 1. Here it is from 0 to infinity. There is one important information you should remember. And there, okay, now you know how to do it. There what we did was that we converted this summation to the integration with the help of the conversion factor, right? What was the conversion factor there? AD is equal to 2 pi V by h cube 2m raised to 3 by 2 e raised to half d. So this was our conversion factor, and we apply that conversion factor also to these expressions, and we convert that to integral. But here, unlike the case of Bose-Einstein case, where we have specially put an additional level corresponding to E is equal to 0, we are not going to put that over here, because we not at all foresee any kind of condensation or any kind of super importance for the 0th level, because the Fermi gas is supposed to be obeying the Pauli's exclusion principle. The Pauli's exclusion principle has put a definite weight to every level, and there can be only 0 particle or only 1 particle, depending on so therefore no two states can have the same quantum number. So therefore we cannot have that kind of a condensation here. So in the integration, we are not specially considering the E is equal to 0 situation here. We just integrate. So in that integration, we will finally get P by KT is equal to G by lambda cube f of 5 by 2 z. Of course, you have the two new things over here. I will explain one by one. And also corresponding to n by v, we can write n by v is equal to g by lambda cube f of 3 by 2 z. Okay. Now let's see what is f there, right? This is a new function we have here. Earlier we used to have the g for the for the Bose-Einstein cases. Here now we have the f1, right? So where f nu z is equal to 1 by gamma nu integral 0 to infinity x raised to nu minus 1 dx divided by z raised to minus 1 e raised to x plus 1. So this is known as the Bose and the Fermi-Dirac function. Right? And we can of course write something similar to the similar expression as we have written for the Bose-Einstein cases as f nu z is also equal to z minus z squared by 2 raised to nu plus z cube by 3 raised to nu minus etc. Which can be written as sum over n is equal to 0 to infinity minus 1 raised to n minus 1 z raised to n by n raised to nu. Okay. And what else we have? We have the g also there. G, right? So what is g? G is the weight factor, which we already know. We have already put those kind of situations in the quantum statistics. So that is that the g stands for. Like in the case of a spin, we have the 2s plus 1, which denotes the internal structure of the particle or the system with which I analyze the Fermi gases. Okay, so now based on this formulation, my intention is to try to see what is the variation of Cv with the temperature for the Fermi gases. For that purpose, first of all, I need the internal energy. Internal energy is equal to U is equal to minus of dou by dou beta ln theta, right, which when expressed in terms of temperature, I can write kT squared dou by dou t of ln theta. I can express it in terms of PV by kT squared dou by dou t of PV by kT. And I can substitute for the P by kT, right? I have already PV by kT. I have already written here this expression for the P by kT. I substitute from there. Then I can write this equal to kT squared G V f of 5 by 2 z divided dt of 1 by lambda cube. So when we do the differentiation with respect to temperature of the lambda cube, finally what I get is that U is equal to 3 by 2 kT GV by lambda cube f of 5 by 2 z. Okay, which I can Okay, this is one way of writing it. Or otherwise, if I need, I would prefer rather to express it in terms of n, right? Because I'm going to discuss on the CV. So let's try to express it in terms of the n. What I will do is that you substitute for the n by v over here, and then I can write is equal to 3 by 2 n kt. I will be helped by, like previously, I will take care of this lambda cube. Instead of lambda cube, I will put the n by v's. In terms of that, we have already done that some time back. F of 5 by 2 z divided by f of 3 by 2 z. Right. So this is the expression possible for my u. And we know that Cv is equal to dou u by dou t. We will do the rest of the stuff to calculate the variation in the next video.